on Zoom can participate. Is Mark.
Okay, thank you so much, Max, for the invitation, for the chance to speak here. It's really a pleasure. Maybe I'll be walking around so the guys on Zoom will lose me from time to time. Hopefully, this hybrid mode will work well. So, yes, yeah, thanks. So, I will. I will have not so many slides, but it will be a little bit of a challenge because I will switch topics very often. So please try to follow along. At first, I will start with a topic somewhat remote from what I actually want to speak about. This is going to be three-dimensional topological manifolds. But I will use that stuff as an analogy and in order to motivate some of the things I want to prove and to talk about. So I need to tell you to present some kind of random collection of facts about the topology and the group theory of three-dimensional manifolds. So it will be just a recollection of certain facts which are not necessarily so closely interrelated. So the first fact that I'll be using, which is pretty classical, is that every three manifold, which is okay, it's oriented and closed, you can realize it as a finite covering of a three-dimensional sphere of S3 ramified along a link, a finite union of knots. Another fact I'll be using is Poincaré duality, a duality in the singular cohomology of a manifold. A third fact that will be sort of very relevant throughout the talk, but for different objects, is the fact that the fundamental group of the manifold admits a so-called balanced presentation. So it's a finite presentation where the number of generators equals the number of relations. So it means that if I take the fundamental group, I can find a surjection from a finitely generated free group such that the kernel is generated as a normal subgroup by these elements R1 up to Rn, whose number is not exceeding the number of generators of the free group. Okay, another fact that I'll be using is a pretty simple presentation for a certain very specific group. If you take a knot in your three manifold, and you take a sort of small neighborhood, the tubular neighborhood of the knot, and you look at the boundary, then the fundamental group of this boundary is just isomorphic to Z cross Z. And I can give it the following explicit presentation, which is probably, if it is correct, it is the most complicated way you can think about it of describing the group Z squared. But it's still true if I didn't do any mistake. But I have some very compelling reason to write it in this weird way because of the next slide. Hopefully you will be able to see why I'm emphasizing this specific presentation. And another fact, so these facts are not so closely related, but another fact that I need is that the fundamental group of the three manifold is always coherent, namely every finitely generated subgroup is finitely presented. So we already saw that the fundamental group itself is finitely presented. Moreover, every finitely generated subgroup is also finitely presented, and it's not always the case that finitely generated subgroups have to be finitely presented. There are some examples, maybe free group cross free group or something like this, but for three manifold groups, this is certainly the case. So most of these facts are classical, proven throughout the 20th century. Maybe only the last bullet point is a little more recent. I think maybe in the 70s due to Scott, and then other proofs also became available. But so all these facts are fairly well known, I would think, by now, and I would use them as some motivation to prove some results about completely different kinds of groups later in the talk. So these are just some recollections that I wanted to make about three manifold groups. So I will not, as I'm always saying, I'm not as interested just in the world of three manifolds as I'm interested in some analogous world, a more number theoretic picture, which is somehow studied by a field called arithmetic topology, where three manifolds are viewed as analogs of rings of integers in a number field. So this is a very vague analogy, but still I find it useful to think in these terms when I'm proving things and when I'm thinking what might be provable. So I replaced the three sphere by the ring of integers, and so you can get finite covers onto the ring of integers by analogy with the first bullet on the previous slide by taking the ring of algebraic integers in a certain number field. So the slides, so the bullets on this slide are supposed to be as analogous as possible to the bullets in the previous slide, but now in the world of number theory. So facts in number theory which are analogous to facts about three manifolds. So the next thing, I need to tell you what the analog of a knot is. And the analog of a knot is simply a prime in the ring of integers of a number field, so it's a prime ideal. So the covering of S3 by a three manifold ramified along a link is analogous to the covering of the spectrum of an algebraic integer ring by another algebraic integer ring in some bigger number field, ramified away, unramified away of finite limiting primes. So ramified only of finite limiting primes. So there is some analogy going on here. And the role of Poincaré duality that we saw on the previous slide is played by quite an elaborate theory developed by several well-known mathematicians. Poincaré duality was a duality theory for singular cohomology. This time, this is a duality theory for étale cohomology and for flat cohomology. You can also get a duality for Galois cohomology.
So in this analogy, the condition of this finitely many unification in number theory, I guess.
Yeah.
There, why then topology, is it a natural condition?
Well, maybe it's not as natural. But I would not, maybe it's not fair. Maybe I should defend the analogy, but I would just say that the analogy is not perfect. So there are many discrepancies like this that you can find, that things are not working on one side exactly in the way they do on the other side. So.
But in your previous slide, you just assumed this condition and you said these are classical.
Yeah, so this is proved by Alexander, I think, late 19th century, if I'm not getting it wrong. Yeah, so this.
They had reasons to take this condition.
So I mean, yeah. So he was able to prove it. I don't think that he thought about number theory when he did that. So yeah, his motivation certainly did not arise in the number theoretic picture. Yeah.
The duality on the previous slide was for dimensions n and 3 minus n.
Exactly.
Yeah,
exactly. This is very good. Exactly the same dimension. So the whole point of this analogy is that the spectrum of the ring of integers in the number field as a scheme, if you want, behaves like a three-dimensional topological object. If you view it from the point of view of cohomology, so whether it's flat cohomology, Galois cohomology, or étale cohomology. So in all these cohomology theories, the duality will be, as you say, between I and 3 minus I, where I goes from 0 up to 3. Yeah, and it's strikingly similar. The only thing, it goes even further than that. So Poincaré duality, the way I stated it, is just with coefficients in Q, let's say, but you can put here coefficients with various sheaves. So it's a quite general thing. Yeah, and so the fundamental group is replaced by the étale fundamental group. And you can define it by unpacking the definition of what étale means and what the étale fundamental group is. It turns out that this is, maybe in simpler terms, the Galois group of the maximal unramified extension of the field L over L. And so it's the Galois group of some quite big extension of L, of some infinite extension potentially of L. Some kind of Galois group of a very big field. That's what the fundamental group is replaced by in this analogy. And so much is known about the fundamental groups of three manifolds, and it is via the lens of fundamental groups that I'm approaching this analogy. So this analogy is certainly very broad and it talks about a lot of things, but I'm specifically interested in this talk, maybe in my research, in the point of view of the fundamental groups. So Shafarevich conjectured that this étale fundamental group, and this analogy suggests that to some extent, is finitely generated. Certainly, we know that the fundamental group of a three manifold is finitely generated, but in this case, we don't even know that this group is finitely generated, and this is quite a difficult open problem. However, Yuan Li recently was able to show that if you assume this conjecture, you can show that this fundamental group is finitely presented, which is what we had for three manifold groups. And so the analogy extends in the sense that she was also able to get some bound on the number of relations that we need, maybe not the optimal bound, but certainly it resembles in some sense what happens for three manifolds. And the proof is also closely related to the analogy because her proof builds heavily on the duality theory that I'm mentioning here, which is an analog, as I said, of Poincaré duality. So somehow, even the proof is in some sense modeled on what happens in three manifold theory. Okay, so later on, I will explain how, try to explain how cohomology and duality in cohomology is helpful in trying to prove that some group is finitely presented. Now we're just believing that something like this exists, but later on, I will try to explain what's the mechanism behind such a proof. How do you use duality in cohomology to prove something about a finite presentation? All right, and now the analog of the last bullet of the fundamental group of the boundary of this tubular neighborhood. So in this sense, the analogy suggests, because the knot is analogous to a prime, maybe a reasonable analog is to look at the local Galois group. So you can take the completion of your number field L at this prime, and then take the absolute Galois group, but it's quite a big group. But you can look at something much smaller, which is just the maximal unramified extension. And it turns out that for the maximal unramified extension, the group is given by this very concrete presentation, which is, in my opinion, extremely similar to the presentation we saw on the previous slide for the group Z cross Z. It's just very slightly twisted by this twist of arithmetic nature, which has something to do with the exact prime you choose. So from my point of view in this talk, one thing that's important to note is that you have two generators in one relation, namely the number of generators exceeds the number of relations by one, in this case of the local group. And the first result of myself that I want to present in this talk is joint work with Moshe Jarden, where we sort of extend this to the entire absolute Galois group of the local field. So now this is a result which can be stated without any reference to three manifolds, or so I could have just given it on the first slide in some sense. But I believe that this is to some extent motivated by, or well motivated by, this discussion of what's going on in three manifolds. So we are able to say, we are able to give for this. So we're just taking a p-adic field, which is a finite extension of QP, and we're taking the absolute Galois group, the Galois group of the algebraic closure over the field. So it's just the collection of all automorphisms of the algebraic closure which fix the base field, the finite extension of QP. And we are able to determine the number of generators and the number of relations. And we are again getting that the number of generators exceeds by one the number of relations, as you might get a suggestion from the theory of three manifolds and from the unramified fundamental group. Just in terms of what was known before we proved the result, there was an upper bound which was available in the literature on the number of generators, and there were certain presentations of the group, but the number of relations in these presentations was infinite. So these were quite explicit presentations, but unfortunately with infinitely many relations in the presentation. The disadvantage, on the other hand, of our result, that the relations are not explicit. We just know that there exist some relations, but we can't quite pin them down or write them explicitly.
Conjecture was.
Oh yeah. So Shafarevich conjecture. This is a previous slide. In the global situation, that this Galois group is finitely generated, and that's a global conjecture about some extension, let's say, of some number field. But our result is about a local field. So we did not make progress, and I don't yet know how to make progress in this conjecture of Shafarevich's.
Your result is somewhat pure.
Yeah, it's about the completion of L, exactly. Yeah. Yeah, so our result is resolutely local. And then this conjecture is quite old by now, and still no one has resolved it by Shafarevich. Yeah, absolutely. So it's certainly possible to view this group as a subgroup of the local group. Maybe it's more precise to say that there's a homomorphism from it to the whole group, but there are many such groups and subgroups inside, and it's not clear to me how they interact. And so I can't quite cook up an explanation for an understanding of the big group from the local pieces. All right, and okay, yeah, so I went over some of these previous results. Another previous result that I should mention is works of Domushkin, Ladut, and Serre, who were able to treat not the entire group, but certain pieces of the group. So you can take your group and take the L part. So this is the maximal pro-L quotient for any prime number L. And they were able to show that these pieces are finitely presented and give some very explicit presentations for these. But again, it wasn't so clear how to take maybe their results and get a presentation for the entire group from these partial informations. In our proof, again, a very important tool is duality in cohomology. Now, because we somehow go to the local group, it still satisfies some duality, which is similar to the one we saw in the previous slide, a special case, in fact. But now the duality lives in dimension 2 and not in dimension 3. So somehow when we pass to the local groups, the dimension drops by 1 in some sense, the cohomological dimension. And this duality in cohomology, which is in some sense some variant of Poincaré duality, if you want, is still very helpful to understand the cohomology. There is this result of Lubotzky that I'm going to mention later on, which allows you to use the cohomology in order to say something about the number of relations. Okay, so another tool we use is a quite elementary bound due to Nielsen and Schreier in order to get a bound on the number of generators, which is a lower bound. The upper bound was already available in the literature, as I mentioned before. All right, so now to the second analogy. So I have already had one analogy, which is quite vague, between three manifolds on one hand and rings of algebraic integers on the other hand. But then there's a next analogy between rings of algebraic integers and function fields. So to speak, rings of integers and positive characteristics. So you replace a global field in characteristic 0 by a global field in characteristic P. So finite extensions of Q, that's what you have on the one hand, and then what you get on the other hand is finite extensions of the field of rational functions over a finite field. So this is the function field analogy. So if you want to talk about this geometrically, then you are talking about the function fields of smooth projective curves over a finite field. And so here it is. So here the analogous fact to Shafarevich conjecture is a theorem by Grothendieck. He shows that the Attell fundamental group is finitely generated, which is a fact that we don't yet know in characteristic 0. We do know it in characteristic P, and this is in fact was one of the motivating results for the definition of the language of schemes by Grothendieck. He was able to quite concisely construct this lifting from characteristic P of the curve to a curve in characteristic 0. And in characteristic 0, a curve can be viewed topologically as a Riemann surface. If you view it as a curve over C, it becomes a Riemann surface. And you understand the fundamental group of a Riemann surface, you get a surjection from that onto your original group. And you get a proof of finite generation. This is one of the first successes of the algebraic geometry of Grothendieck. And then just a small piece of motivation for why we are interested in these fundamental groups. How much do they know about the objects? So in the 2000s, maybe a decade and a half ago, Mochizuki was able to show that you can functorially reconstruct any curve over a finite field from its fundamental group, which is quite remarkable because usually many different topological spaces can have the same fundamental group, but somehow for curves over finite fields, the fundamental group remembers the structure of the variety of the scheme, which is quite remarkable. So certainly studying this object is going to tell you a lot about the curve itself. And the main result here is sort of similar, although less explicit. I have proven some 3 years ago now that this group is finitely presented. Moreover, the number of relations equals the number of generators. Although I cannot quite say what is this number of generators. I can give maybe an upper bound and a lower bound, but I haven't yet proven that it is this or that number. But still, I can show that it's finitely presented, and I can tell you that the number of relations is equal to the number of generators. And then this builds on somehow one of the inputs is this theorem of Grothendieck. There are some other inputs. Among them is duality and cohomology, again, something which follows from this analog of Poincaré duality in this case. and having some motivation from three manifolds, I was able to show that this group, this fundamental group, is coherent, namely every finitely generated subgroup is also finitely presented. So this result about three manifolds somehow carries over to this world, and also we know again that the number of relations equals the number of generators, which is something we saw on the first slide about three manifolds. Somehow, and I can certainly say about, because this is my result, I can tell you in complete honesty that I was motivated by these facts from the topology of three manifolds in order to make the statements. Otherwise, I wouldn't probably have thought about trying to prove these statements because I wouldn't know what to expect.
Another question as well, or
No, the proofs are completely different somehow. Yeah, so in this world of so this result does build on cohomology, which is I'm trying to say in every slide is an analog of some Poincare duality which comes from three manifolds. But the proof of a finite presentation in three manifolds is not cohomological at all. It proceeds by some different arguments. You need to construct this Heegard splitting of your manifold and arguing in a different way. But somehow, so the proofs are very different, but the tools I'm using here are coming from the theory of three manifolds nevertheless. Yeah, question.
Would all out of the banner of finite theorem, the fundamental root of three manifolds. And another famous one is that their fundamental root of three manifolds are residually finite. Do you know anything about the residual finite?
Yeah, so I was tacitly trying to hide the fact that these groups are profinite groups throughout the talk, but now I don't have any option to hide it anymore. So yes, they are. So these are these are profinite groups. They are residually finite. Yeah, and there are others. So this is a very good point. So I have read about some other facts about three manifold groups, which you might wonder whether they are true in this case. But I don't yet know what the right analogy is, because you see in this case it's somehow vacuously true, but it doesn't mean that there isn't some more sophisticated question that is really hiding here. So I really don't know. Yeah. So there are some other questions which I don't know how to create the analogy of. And so some of the motivation for caring about why these groups are finitely presented, so why do we care about that so much? So some reason is it again originates from the study of fundamental groups. In topology, sometimes you're interested in the representations of this group, and you can construct a certain character variety or representation variety. And for that, it's tremendously helpful to have a presentation for the group. Because then if you want to study a homomorphism into some specific GLN, then knowing what the relations are is very helpful for knowing what the homomorphisms are into various concrete groups. If I could get some very concrete handle on this group, I would also be able to say maybe something about their representation theory, which is something that people in the Langlands program care about very much. But I don't yet have any applications of that sort because my presentations are very far from being explicit. Okay, yeah, and so now a third analogy, if you want, it's very natural once you have obtained a result for varieties of dimension 1, namely for curves in characteristic P, try to prove something for higher dimensional varieties so this is my X. Now a smooth projective variety of any dimension. And it turns out that you can obtain an extension of that result. So first we need the fact that the fundamental groups of these varieties are finitely generated. If they lived in characteristic 0, that would be much easier because in characteristic 0, I can always switch to any algebraically closed field. Yeah, so I say, yeah, so this, okay, now I see that the slide is not super precise. I should have said if X lived over an algebraically closed field in characteristic 0, then it would be more precise. You can always switch to the complex number in this case without changing the fundament, the étale fundamental group. And then if you look at the collection of complex points as a topological space, you can show it's homotopic to a finite CW complex, and the fundamental group of any finite CW complex is finitely presented. So somehow not super hard to read off from the complex itself. And then by a Riemann existence theorem argument, you can conclude that the étale fundamental group is also finitely presented, being the profinite completion of the usual fundamental group. So if the usual fundamental group is finitely presented, its profinite completion is also going to be finitely presented. So I'm mainly giving this argument, so somehow, yeah, I'm giving it in detail, but in fact, I just in order to say that I can't use anything like this in characteristic P, because I don't quite have this notion of homotopy, and I can't quite look at the topological space, and I don't have anything like this, yeah, which is exactly like this in characteristic P. So something different is needed, and so again, as on the previous slide, finite generation was available to us by a result of Grothendieck. This is some extension of what happened on the previous slide. The additional input that you need is a Lefschetz hyperplane theorem in order to reduce the dimension of the variety until you hit varieties of dimension 1, which is curves, and then you get the result of Grothendieck from the previous slide. So Grothendieck extended his results to a higher dimension and proved that the étale fundamental groups are finitely generated. And the result, yeah, and so the result that I want to present in this section is my joint work with Helena Noe and Untitled. We have proven that this étale fundamental group is finitely presented. Okay, so here again on the slide there should have been an ET for étale for this pi1 of x, because I don't have another fundamental group but the étale fundamental group. So also I put on the slides some previous result in this direction, which is also similar to what we had for local fields, some previous result of the same sort. So it is originally due to Raynaud, and then in the strongest form by Orgogozo some 18 years ago or something like this. He showed that the maximal pro-L quotient, so again some part of the fundamental group, is finitely presented. And this is again a special case of our result. And here, important restriction in this theorem is that L is not equal to P. So for example, they were not able to treat, in some sense, the P part of the fundamental group, where P is the prime, which is the characteristic of the field over which the variety is defined. Yeah, and so again, as in all my previous slides, a very important tool is this duality in cohomology. Some sense now that the cohomology is going to grow to arbitrary dimension because I'm working with varieties in arbitrary dimension, but nevertheless, it's possible with this Lefschetz hyperplane theorem of Grothendieck to reduce to dimension 2, where you don't have so much cohomology, and then make a comparison between the cohomology of the profinite group and some tau cohomology and coherent cohomology. And for these cohomologies, we have several duality results, which are very helpful in bounding the cohomology and obtaining a finite presentation for it. And I will, on the next slide, finally explain what is the connection between cohomology and finite presentation. Right? Any questions about that? All right, so somehow maybe it was not a very good idea to keep the main ingredient to the very end. Maybe I should have somehow presented it in some earlier point. Maybe that would make things more understandable, but nevertheless, that's what I chose. This is, okay, yeah, you just put this. This is this result from Lubotzky like 20 years ago or so, which gives us a very explicit criterion for a profinite group to be finitely presented. And this criterion is resolutely cohomological. All you need to do, once you know that the group is finitely generated, which is certainly a prerequisite for being finitely presented, all you need to do is to bound some cohomology groups in a strong enough fashion. And here it's all the more crucial that we're dealing with profinite groups and not with just some arbitrary discrete abstract groups, because for discrete groups, there seems to be no criterion that we know about that would tell us that a group is finitely presented just on the basis of bounding its cohomology. So this result of Lubotzky is extremely special to profinite groups. So this is somehow crucial that all the groups I've been working with throughout this talk are profinite groups. And so you need to control these cohomology groups. And somehow this is where Poincaré duality kicks in, all the versions of duality I've been mentioning, that in order to get the result without a finite presentation, we are shifting this cohomology in dimension 2 to cohomology in some other dimensions where it is more manageable. Or another strategy that we're using is to complete this cohomology into an Euler-Poincaré characteristic. So maybe you don't know the cohomology in degree 2, but that's the only thing that prevents you from knowing the alternating sum of other cohomologies, because maybe the other ones are more manageable. And then the Poincaré, the Euler-Poincaré characteristic admits various formulas, such as the ones I've mentioned on the previous slide. And so these are the techniques that we're using in order to study these second cohomology groups. And in fact, Lubotzky's paper gives a more precise formula, which in fact involves the Euler characteristic or some truncated Euler characteristic. It says that, so basically it gives you a formula for the number of relations in terms of this cohomological data. So this second formula I'm presenting is supposed to be more precise than the first one. The first one just says that the number of relations is finite, but this one tells you exactly what the number of relations is. So how one way to state this formula is if you take a presentation complex, so to speak, for your group, and if you take the Euler characteristic of this complex, namely number of relations minus number of generators plus 1, then this thing magically equals to some other kind of cohomological Euler characteristic. But you need to somehow range over all the primes P. And here V is the same thing which it is on the previous bullet. It's some finite dimensional, irreducible, if you want, representation of this group G over this finite field FP. And so using this numerical recipe, you're able to say how many relations you have, and in all these results that I mentioned, what we're doing is to compute this thing, or to upper or lower bound it for every prime P and for every representation V. Perhaps another thing that's worth mentioning about these computations, which I maybe haven't quite mentioned yet, is that even though we're working over doing the Superman over all primes P, it's not quite uniform. There will always be one nasty prime which will be the hardest to work with, depending on the situation in which you're working. So in one of the first results where we talk about a local field, it has a residue characteristic P, and then this P for the group will be the hardest. Or when the this smooth projective curve or variety is defined over a finite field, the characteristic of this finite field is going to be the troublesome prime for the group. And this prime is going to be the hardest one for which you need to analyze this truncated Euler characteristic. And somehow most of the work, which I can't quite go into today, goes into dealing with this nasty prime P. Okay, yeah, I think so. So for today, that would be it. Thank you very much for your attention.
Once you give some concrete presentation complex or something concrete out of the cohomological groups?
Yeah, so actually, this statement is not written in the paper of Lubotzky. Somehow, this is the way I reinterpret the result of the paper. Lubotzky just writes number of relations like R equals 2, and then he puts the D on the other side, and then he apparently doesn't quite notice that there is an H0, but he writes it in like some equivalent way. So the way I write it is quite funny because H0 is like just the number of fixed points, but if it's like some honest irreducible representation, there will never be fixed points. So it will just be 0. So it's just like not there. So he doesn't write it in terms of Euler characteristics. This is just, I guess it's just like the way you prefer to write it. So he somehow just directly proves that it's true without any geometric argument with any presentation. Yeah, so in fact, when I'm saying a presentation complex, I don't quite know what I mean because presentation complexes only exist as far as I know for discrete groups and not for profinite groups.
Okay. My question is maybe, can you write the equations?
Yeah, go ahead. Not that I know how. So sometimes in profinite groups, like I guess, even if you think about, like, let me give you an example. So a free pro-solvable group is some kind of very concrete profinite group, which is given by, like say 5 generators, it depends on how many you want, and one relation. But no one has yet, as far as I know, written down this relation explicitly. So even though it's quite explicit profinite group, I'm not sure I know, maybe I'm just embarrassing myself in front of everyone, but I don't really know how to write this relation. So profinite relations can somehow have infinite length, but we can some quite weird profinite words. It's not always super easy to write them down. So yeah, so this, as far as I know, it only tells you about the number of relations, not about their nature, how to write them down and so on. Yeah, exactly. So for finite groups, it is conjectured to be the same, but most of the groups somehow I talked about today are not finite groups, and you won't have a number of abstract relations for them. Yeah, but that's one of the big conjectures, yeah, in this area.
So by generators and relations, we mean that you take some free finite group and
Exactly, yeah. Yeah. So you take a free profinite group on, so suppose it's a group generated like by 5 elements. So you take a free profinite group on 5 elements, you map the generators that, you get a kernel, which is a normal subgroup, and then you take the least number of elements which generate the kernel as a closed normal subgroup of the free profinite group. And it turns out that it doesn't depend on the specific presentation that you choose. It turns out for profinite groups, at least for most of them, these numbers, the number of relations, so suppose so this number that I wrote, r minus d, okay, you can remove the plus one. This r minus d, which is usually called the deficiency or the negative deficiency in group theory, it doesn't depend on the actual presentation you choose. So suppose you pick some extra generators and do something very complicated, still the deficiency is always going to be the same. And that's, again, something which is very special to profinite groups. For discrete groups, you can somehow mess this up and change the deficiency by passing to some more complicated presentation. But for profinite groups, this formula is literally valid for every single presentation of the profinite group.
Is there any analog to Euler splitting this?
I would love to, yeah, I would love to find it. Yeah, that's a great question. Yeah, I don't know how, maybe for some special cases, but yeah, it's certain, there are certainly many things about three manifolds that I would really like to understand what's the analog for any of the stories that I've been presenting today. Yeah.
Then it could be Poincare conjecture.
Oh yeah, that's a good question. So they figured it out at some point. So the analog of S3 is Z, and so the analog they came up with, which maybe you can agree with or disagree with, is if you have some ring of integers, I guess whose compactly supported the tau cohomology satisfies what the analog is of something on S3, then it has to be Z. But I won't get into the details of that because it's somehow, you see, it's somewhat controversial because it's not a super close analogy necessarily. So maybe someone can say that it's not the right analog.
People really view it as a conjecture.
I think they proved it. Yeah. I think, yeah. But maybe I'm forgetting something, but I thought they proved it. Yeah.
The analogies.
Yeah.
Lines, particles. So all of them will write a computation. They can set explicitly how many relations, except for the middle one. The lines, so there is a finite computation.
Yeah.
Somehow we can actually say that.
Yeah. So one reason is somehow my ignorance, because maybe I haven't studied Yuan's work sufficiently closely, but maybe it's possible to, so she obtained a certain number, but the number she obtained is an upper bound on the number of relations. And so maybe you have a reason to suspect that a better bound might be available if you study the cohomology more closely than she did, but maybe she got the right numbers. I'm not completely sure. But yeah, there is some number. Only in her result, as opposed to the other results I presented, it's only an upper bound of the number of relations. Yeah, as opposed to like the exact number.
So, once you really know the relations with 5, 4, and 3, you just know truncation. Know how the relations are.
Oh, yeah, that's right. Yeah, we do know the trinket. Yeah, that's a good point. Yeah.
Then you do expect almost equality. Just like the other. And I don't know what's known about quality.
Well, wait, I think I did follow the first. Yeah, so you know the truncations, but then what do you want to infer something from the truncations or?
So on the level of the big oceans,
Yeah.
you know D is equal to R. Because you have done certain basis to things like this. And you know the number of generators from the relation.
Yeah, but you know, yeah, but I don't. Wait, but I don't think it's. You don't think you.
But that's just the equation.
Yeah. Right. Exactly. Yeah. Yeah, but sometimes I was just going to say that sometimes when you pass this pro-p quotient, even the number of generators and relations can just can just change. You don't, it's not all like always the same number. So sometimes even that you can't get. But I agree that sometimes you do get the right numbers from the pro P. Yeah, that's right.
These bonds that you're proving, you said something. Do you need to know something about the presentation theory of G?
Unfortunately, yeah, unfortunately not. So it turns out you're able to get away without really knowing which V can appear. So in all those results, the maximum, if I remember correctly, was attained by one of the simplest, like maybe the trivial representation or something.
More precise information, like sharper bounds would be better information. More into
yeah, so I can certainly imagine that for one of the groups that I can't succeed with this method, a knowledge of representation theory would help me. But yeah, but I don't, yeah, so that's the problem. When you go to a talk, you present the cases where you did succeed. And so for the cases that I don't succeed, probably yes, the representation theory is going to be helpful, but I just don't know how yet. Yeah.
Is the constancy important? Like, does it have theoretical significance?
Oh yeah, so I mean, in the second formula, the constant C is what is going to tell you what the number of relation is somehow hiding there. But yeah, so the point of stating it like this, so that if you just want to prove a finite presentability, so this is somehow, yeah.
Then you don't care.
Yeah, if you just want to, yeah.
But it gives you the discrepancy or the.
Yeah, exactly, yeah.
Thank you, Mark, again.
Thank you.
Recording.
All right.